Alright guys, let's look at Newton's third law. This is going to be take 3 of this video. So, in any case, I'm going to go through it. You're welcome to go at your own pace. But I will say is, I want you to be of good kind of mental spot when you're taking these notes, because these are going to be have a little bit of nuance, a little bit in depth. So I want you to really be ready when you're ready. Okay? No backseat learning today. All right, what do we know? We know F net equals 0 means you're either going at constant velocity or not moving. That's what we know for so far. If F net does not equal 0, then that means F net equals mass times acceleration. You're going to be accelerating. From there, we also get that weight equals mass times gravity. Okay, we're going to be using these things today, Newton's first and second law, and kind of wrapping it up a little bit with Newton's third law. But with that, let's move forward. What is Newton's third law? Well, Newton's third law says for every action, there's an equal and opposite reaction. What does that even mean? So let's do force due to any action is going to be equal and opposite to the force of a reaction. Now, I've seen this written like this a couple ways. I don't quite like it because students will get FA, or you guys will get confused with it. FA is force due to acceleration for some reason, or force applied, when it's really force of action. So what I'll say is I want you to list the objects as they were if it helps you out. So we're going to say from here the force of a finger is going to be equal and opposite to the force of the wall. Meaning the force I put on the wall with my finger, or my other hand for example, is going to be equal and opposite to each other, regardless of what happens. If I push so hard that my finger goes through the wall, the forces are still going to be equal and opposite. They cannot be more, or they're not going to be anything different. But is this true actually? Well, let's look at it. Let's go through this example. So I want you to pause the video real quick, read through this, and think about how is Newton's third law still true in this instance? All right, hopefully I'll pause the video. I'm willing to bet you didn't. But in any case, I'm moving forward. If we have a bug and it gets hit by a windshield of a bus, here's my wonderful bus with a small engine, and the bug hits the windshield, the bug is going to apply some force, we don't know what it is, doesn't really matter, to the windshield. And the windshield is going to apply an equal but opposite force to the bug. So we'll call that the bus. Well, what do we know? We know that force equals mass times acceleration, Newton's second law. So let's do a lowercase m for mass of the bug and a capital M for mass of the bus, because we know the bug is going to be smaller than the bus. If not, that's some really big bugs out there, or some small buses, but I digress. Well, force equals mass times acceleration. We still have Newton's second law. If force equals mass times acceleration, then the bug, in order for this to be balanced, must have a huge acceleration. And the bus is going to have a very small acceleration, almost 0. Technically not 0, but we can essentially say it's 0. But there's one thing in here that needs to be brought up, and that it's still going to be a negative relationship. They're always going to be opposite to each other. So does Newton's third law hold true? Absolutely, always. You can't break physics. It might break you. So let's look at some case studies or some examples of Newton's third law in action. So you're welcome to read this. This is kind of an equal example, but using a truck and a train rather than a bug and a bus. You're welcome to read through it, but I'm going to move on. Okay, I'm going to look through these examples, and I want you to follow along with me. I do want you to notice that I'm going to use 5 kilograms on the mass rather than 50. You'll see why in a second, but anyways. What I want you to do is, this is a refresher. So I actually want you to pause the video, Try this out on your own. See if you do it right. And if so, looking great. If not, watch this part of the video. So since this should be a refresher, I'm actually going to kind of blast through it a little bit quickly, but still explain all the parts I got going on. Well, what do I know? I know that I got a little part over here I need to erase. Here we go. I know that when a student moves a box horizontally with a rope to the right, tension, since it's a rope, is going to be 150 newtons. I know there's a downward force called weight, which is mass times gravity. There's an upward force called force normal. And there's a force to the left called force of friction. Boom, done. There's all my forces. But now let's find a number for them. Well, we've already got tension. What we don't know is if the object's moving at a constant velocity or if it's accelerating. So I can't say that these friction force and tension are equal. I can't say that. So let's try to do things that we do know. Well, we know weight equals mass times gravity, so that's going to be 5 times 9.8. What's 5 times 9.8? Well, that's 49 newtons. So force normal equals 49 newtons. Because my box isn't falling through the air, it's not flying up in the air, or falling through the table, flying in the air, we know that the forces up and down are going to be equal. Well, what else do we know? We know mu, the coefficient of friction. So we can actually find a number for frictional force, and then we can see if it's accelerating or not. So, frictional force equals mu 0.5 times force normal, that's going to be 49. 0.5 times 49 is going to be 24.5 newtons. So we find out friction is 24.5. That means not balanced. I got 24, let's say 24, 25 to the left, 150 to the right. Means F net equals MA. Our forces are not balanced. So let's try it out. What do we have? We have tension. We have frictional force. Since they're opposite, we're going to subtract them. Mass, acceleration. Tension is 150. Frictional force is 24.9. Mass is 5. Acceleration. Cool. 150 minus 24. Oh, I don't know why I put 9 there. It's a 5. 24.5. I did put a 9 over here. That's okay for doing these late. It is currently past my bedtime. So 125.5 equals 5a. Divide both sides by 5. We get acceleration to be, let me think mental math. 25. That's going to be 25.1 meters per second squared. Survey says, let's see. Hey, look at that, I did it right. We're accelerating, and we found a lot of forces. Boom, we're done. Okay. Now, let's try looking at angled forces pushing down on an object. So before I kind of even unpack this at all, I want us to draw what's going on first. We got a hockey puck. So I'm going to color in my hockey puck. And it has a force applied to it at a downwards angle. What I want you to do is I want you to pause the video and I want you to try to draw this free body system on your own. Read through the questions, chew on it, see where you get, okay? In the meantime, I'm going to erase this and I'm going to put this actually right here. And you'll see why here in a moment. Okay. What forces do we have working on my object? Well, we got a downward force called weight. we have an upward force called force normal. And we also have our components, or our parts of force applied. So this force right here, let's do that, let's do yellow. We're going to have a force in the x direction. Oh, let's see if I can actually move this down a little bit. Well, let me move it down. Oh, it would. If I could select all the pieces at the same time. I'm not going to do that. That's looking too ugly. Let's go back to the problem. This is force applied in the x direction. And this is force applied in the y. You know what? I'm going to erase it. You can just skip on ahead. Look at that. That's the point of the video. You can skip on ahead. I'm going to redraw my puck. I'm going to redraw it down here, because I'm going to run out of space, and I do want to make sure I have enough space to write things in nice and clearly for you guys. This is my third take on the video, so I'm not going to go back. Force applied, downward an angle. I know we have weight downwards, force normal upwards. I know I have this force applied is going to have force applied in the x direction and force applied in the y. Notice how I wrote that. Force applied in the x direction and force applied in the y. Okay. So what do we see here? Well, if I'm pushing down with the puck, what does that do to my environment? What does that do to my system? Okay. Take your hand for me. Let's do a little mini experiment. Okay. I want you to take your hand, and I want you to gently rub across your hand with each other. Okay. Notice the amount of friction there. Not a whole lot, but if I push into or pushing down on my hand while going across, we notice that friction is going to increase. Okay. For this problem, however, to make sure it's not going to be too crazy for us, we're going to assume friction is 0, because we don't on some ice. So what we know is friction equals 0. We did not include it on there, but I do want you to kind of see, if you push down, what does that do to your friction though? If this was a different kind of problem, friction increases. All right, how do you guys? Let's look. How do I find the acceleration of the system? Okay. Well, in the y direction, when you push down on a hockey puck, your hockey puck doesn't go through the ice and it doesn't fly in the air, especially if you push down. So we know is that all the forces in the y direction, up and down, are balanced. Well, what does that mean then? Well, that means the only thing that are causing forces are going to be in the x direction. Mass times acceleration. Well, what is F net? F net would then be force applied in the x direction equals mass times acceleration. Do I know force applied in the x direction yet? No. We do know force applied though. Anytime you see an angle, folks, what are we going to do? We're going to do some trig. So I'm going to redraw my trig triangle. Let's redraw it over here. That's 60 degrees. I know this is 10. We're looking for force applied in the x direction. That's going to be cosine. So we got cosine of 60 equals force applied in the x direction over 10. Force applied in the x direction equals 10 cosine 60. I've only been talking for 15 minutes. Wow. Feels like longer than that. Well, I guess this is the third time I've done this video. Did I say that yet? I think I did. 10 cosine 60. I believe that's going to be fine. Yes, I know my trig. So force applied in the x direction is Oh, I'm running out of space here. Make sure I'm not. See if I draw a line. So that goes in the video. If I do that, I apologize. But force applied in the x direction equals 5 newtons. So 5 equals 0.5 acceleration. Divide both sides by 0.5. You get acceleration to be 10. That's right. 10 meters per second squared. Cool. Done. What if, instead of pushing down, I pull up? What if Grandpa pulls up with the force rather than pushing down? What I will say, though, is that Grandpa's going to pull with just enough force that force normal is going to equal 0. He's going to lift up with just enough force that the sled doesn't pick up off the ground, but we're going to say force normal equals 0. It should say this in your homework. If it doesn't, say, hey, Mr. Williams, you done me bad. You done me wrong. Some of you might already just feel that. In any case, there we go. Let's draw a sled. My wonderful sled. Grandpa's pulling it at an angle upwards with a force of 100 newtons with an angle of 30 degrees. So let's undo that a little bit because that's going to get in my way. I'm going to do the same thing I did earlier. I need more space. Let's erase it. There we go. I'm draw it down here. I should learn. I don't learn. Let's draw a sled. There's my little sled rails. Put little curves on them. And then we're having a grandchild, so let's draw a little. There's a grandkid chilling in the sled. Grandpa's gonna pull. Not a very straight pull. This is a wonderful picture. Grandpa's gonna pull at an angle of 30 degrees. Find all of the forces here. So we're going to say, since I actually tell you we're going at a constant velocity, we know F net is also going to equal 0. So that means my forces up equals my forces down, and my forces left equals my forces right. So let's draw all of our other forces in there as well. So we got force applied. That's going to be up at an angle. We got weight. I say force normal. I tell you in the question it's 0, so force normal doesn't exist. But we do know is that there's going to be a frictional force to the left. Okay. If we were to break into our components, we know we have force applied in the x direction and force applied in the y. We have force applied in the x, force applied in the y. Let's now unplug or figure out what's going on here. Since F net equals 0, we know that the force is going up, force applied in the y direction, equals the force going down. And the force going left equals the force going right. That's it. Boom, done. But we got to figure out our numbers. Okay? Let's try this out. Well, what is weight? Weight is mass times gravity. The weight mass of the child is 65. Gravity is 9.8. So that tells me 65 times 9.8. 637. Poop. You know what? I realized I just made a boo-boo. I thought I caught it. I didn't. FNet can't be 0. It just can't. Because how the math is going to play out, I'm either going to break the laws of physics or correct my problem. I'm going to do that. So let's throw FNet in there now. Force normal. Alrighty. From here, we should be able to find the rest of our forces. So what do we have? We have force applied in the x direction. We have force applied in the y direction. We have weight. We have frictional force. We got 1, 2, 3. Oh, we have force applied. Yeah. We know force applied is 100 newtons. We also know that force applied in the x direction equals frictional force. Oh, we just found weight. Weight is 637. Okay. Let's try to find the rest of these. Man. We do have to change one thing here. Man, that's a bummer. Since we have 2 forces going up now, I guess we should have 2 forces going up. Boo. Alright. I'm going to squeeze this on over a little bit. Let's draw our trig triangle. Our angle is 30 degrees. We know this is 100. So finding Fy, force applied in the y direction, force applied in the x direction, we just do some simple trig. One's going to be sine, and that's going to be force applied in the y. So force applied in the y is going to equal 100 sine. Oh, I'm squeezing out of the frame. Gotta get back in frame. No! There we go. Sine 30. We also know that force applied in the x direction is going to be 100 cosine 30. At this point, you should be able to do that part on your own. But what does this mean? 100 sine 30. 100 sine 30 is going to be 50. I should have known that. I really should have. And then 100 cosine 30. This is going to be an ugly number. That's going to be 86.6. I'm out of frame again. Hot dog. There we go. All right. What do we know? We know force applied in the y is 50. We know force applied in the x is 86.6. Well, what does this tell me now? We know force applied in the x is equal to force of friction. So that means friction is also now 86.6. And we are one step away from finding the last one, and that would be force normal. Force normal equals plus 50. Ah, that's looking ugly. Let's redo it. That's looking ugly. Force normal plus force applied in the y direction is 50 newtons equals weight, which is 637. So force normal equals 637 minus 50, which is 587 newtons. So there we go. We found all of the forces involved. Man, it's looking a little bit like Christmas over here. We found all the forces and all the components of this system. Okay. Alright, we got one more problem to do, and we'll be done. Okay. Now, this deals with a mass sitting on a slope. So rather than pushed on a slope, being pulled on a slope, doesn't matter. This doesn't quite pertain to your homework. So honestly, if you just want to focus on that, hit pause, be done with those. I would be okay. However, if you want to push the envelope, do awesome. Be awesome. Understand physics. You're going to chill me on this problem. If you don't want to, that's okay. I'm not hurt. Alright. I want you to pause. If you're still sticking with me, you're awesome to begin with. Alright. I want you to look at this problem and try to draw a free body diagram of an object sitting at a slope. Okay? Pause. You try it, and then once you think you got it, hit play. Okay? Weight is straight downwards because gravity's still downwards. What about up the plane? Well, since the box wants to slide to the right, that means friction has to be up the ramp. Since friction goes up the ramp, right, or since the box wants to slide down the ramp, friction has to go up the ramp. What about perpendicular to the surface? That is force normal. Because normal means perpendicular to. And what does perpendicular to mean? Perpendicular surface. 90 degrees. Okay. Now I'm gonna do a little bit of trickery here. Okay. We've got all of our forces in here. Draw a free body diagram. But where does my angle play into fact? Well, we're going to have to break our weight into components. So if you take your head and tilt it to the side, what you see is force normal is going up, friction is to the left, and your weight is your angle. So this is my angle right here. Okay. What are these components called? Well, this is weight parallel to the board, and this is weight perpendicular board. I know that's going to feel really, really weird, but stick with me. Okay. All right. Oh, this is so much fun. I like this. This is real physics. All right. I'm going to redraw that triangle like so. There's my angle, 20 degrees. Actually, you know what, let's redraw the way it is on here. So we got weight going downwards, weight perpendicular, weight parallel, and this is just weight. Well, I say the weight of the box is 500 newtons, and my angle is right here. This is 20 degrees. Which trig function would I want to use? Well, if I'm trying to find weight parallel, that's going to be sine. So sine of 20 degrees equals weight parallel over 500. And then cosine 20 equals weight perpendicular over 500. Weight parallel equals 500 sine 20. Weight perpendicular equals 500 cosine 20. Oh, where did I get 20 from? The angle's 30. I'm just gonna just make the angle 20. Oh, look at that. Nobody can argue with me. I have the whole power. 500 sine 20. That's going to be 171 newtons. And weight perpendicular equals 500 cosine 469.85. All right. What does it have to do with anything? Okay, let's look at this. If we look at weight perpendicular going into the board, what is coming out of the board? Force normal. So what I know is weight perpendicular actually equals force normal. We found force normal, and that is 469.85. What else do we know? We know weight parallel equals force of friction. But why is that? Well, look, weight parallel is going to the right. What's going to the left? So friction force equals, where's that? 171. Boom, done. But we gotta find the coefficient of friction. Well, we have the information we need. Gosh, I love physics. It's just so great. Oh, let's do it black. Force of friction equals mu force normal. So 171 equals mu 469.85. So mu equals, what's 171 divided by 469.85? I get 0.36. No unit, remember? Coefficient of friction is no unit. What does this mean? Well, that means the coefficient of friction is that number. But why is it that number, and why were we able to say some of those things? Where's my thing? There it is. Okay. We were setting a mass on a board, and we were lifting it until it just begins to slide. Since it just begins to slide, that tells me that the friction, the maximum friction it can be, was overcome. And the maximum friction it could be was that 171 number. Since we knew the maximum friction and we knew force normal, we could find the coefficient of friction by having an object slide down a ramp. Okay, this was a lot to unpack. If you have questions, absolutely, I'd love to help you out. If you made it this far, high five. Come over and whisper and say, hey, Mr. Williams, I got through all the notes. And I'd love to give you a piece of candy. All right, you guys are awesome. Stay awesome. This is some real physics. Okay, I'll see you guys on the next video. I'll see you in class. I'll see you when I see you.